tell me you guys keep making the same mistake throughout the whole semester. Even just 5 students in the class is still a lot of grading. I could imagine if I have like 20 students. I'm not blaming the faculty members who are using TAs, so I totally understand it. Since I only have 5, so I can say that. If I have 20, I'm gonna find a TA definitely. So the quiz first. So the square law equation IDS equals KPN. This is n moles. You can see there's no bubble here, so it's n moles. KPN over 2 W over L VGS minus VTH N, which is 0.8 volts. That's the voltage we have been using all the time. Because we use beta N to represent KPN times W over L. So IDS also equals beta N over 2 VGS minus VTHN. And move 2 to here to the left. So you got 2 IDS and 2 IDS divided by beta N and square root of it, and then plus VTHN, you got a VGS. Let's do it step by step. So this becomes 2 IDS equals beta N VGS minus VTHN square. Okay, so 2 IDS over beta N equals VGS minus VTHN. And then square root for both sides of the equation, because I know this is positive, right? This is being operating in the saturation region. So this really doesn't matter because this is already given. If I have IDS, I can find VGS. So this is not, you don't have to consider this at all in this case. See this equation, the square law equation? If you have IDS, you got a VGS. Okay, so we are here now. Square root for both sides, you're getting 2 IDS over beta N. This equals VGS minus VTHN. And then VGS equals this is actually an equation you should remember or should memorize. Next time, if I give you an ID and asking you IDS, you shouldn't go through the process again. It takes so much time. You should directly just hide it here. So what is VGS? What is VGS? 2 IDS over beta N square root plus VTHN, right? Try to memorize it. Okay. Now, the most difficult part. Most everyone reached here. But after that, you see all different calculations, all different numbers being calculated. So I have to blame middle school math teachers over here. Okay. So what is this? 2 IDS is that 16 micro. It's 8 microamps, so 60 micro over beta N. This guy, right? It's 120 micro times 20 over 2, which is 10. So it's going to be a 1200 micro. I'm just ignoring all the standard units. So this is amps over V square, I think. So this is 16 microamps. Let's just ignore it for now. Let's just put it in here, it doesn't matter. So this is 1200 microamps over V square, okay, and plus 0.8. This makes sense because current, they're getting canceled, and you got a v square. V square square root, you got a v. So v plus v, still v, right? So 16 over 1200 gives you what? Like 0.013, I think. That's the calculation. So it's 16 over 1200, right? And square root. Wait, so this is correct. Why shows a different number when I used my phone? So some of you made it right, I think. Okay, so this becomes 0.115. Did you made it right? Did you made it this number? You did it? Okay. You guys? No? Hmm? Oh, yeah. I'll give you more points on that, okay? Okay. We'll do it again on Wednesday. What you want to do? I mean, we'll consider later, okay? So we see which one has a higher score. Okay. 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 Interesting. My phone's calculator gave me like 0.3 or something. I don't know. All right. Wait, there's something wrong with the calculator? Let's do it one more time. 16 over 100 square root. Okay. It's about right because this is about 10%, right? So 10% of 10% should be 0.01. It's pretty much that number. It should be pretty accurate. Okay. Right. Next one. See, cross section is 3, right? I did ask for 1 and 2, so just draw 3, whatever for this dashed line. So here is the most confusing part. So what does P select do? So let's just repeat it for a few more times. Remember in the lectures I talked about P select. So P select let's write it down here. So active. So P act opens up Fox. So select dope N plus or P plus. Remember this, okay? So this is a little bit confusing here. So I got a P select covers the entire area here, and the P select is going to dope N plus or P plus. Is this a PMOS or NMOS? P select, so it's a PMOS, right? That's why we got N well here. So the whole thing is being doped in N well. Okay, so definitely when you are drawing the cross-sectional view, you need to draw the N well first. And then it's a PMOS because you have a gate in the middle, you have 2 diffusion areas. So how to draw that P plus? I should cover this a little bit in the lecture. Probably you forget it. So when you dope P plus or N plus, you actually put a gate on the top first. Okay, and then you dope the material. So it's going to directly dope the material here. So it's self-aligned because the gate is in the middle, so it's blocking all the P plus in the middle, and it's just the self-aligned. The gate and the P plus are self-aligned here. You don't have any P plus underneath this gate because it's blocking the P plus material from reaching that P substrate. So that's why it's just at the edge here, you have a P plus because this guy and the P plus, the three components are self-aligned. You don't have to dope this first and then place a gate on the top. There's no way to do that because these are nanometer scale. There's no way that you can make it accurate. So I have to put a gate here first, then dope it. Okay, so when you're drawing this cross-sectional view, you know that the whole thing here, right, this area is what? What is this? That's a P plus. What is underneath this gate? What is this area? And well, yes. What is this? P plus, another P plus, right? And on the top of P plus, you have a few vias, right? So the vias will connect to the top to metal one, so you can connect the signal upward. This is from bottom up fabrication process. So we got a P plus for this line, okay? For this line, do you have P plus in here? So let's draw this cross section 3. So we got a substrate first, okay? So we cut it and then we look from the side like this, right? So what's happening is you have unwell. Yes, we got unwell. Do you have the unwell all the way to here? No, you don't have any unwells here anymore. But the dashed line was drawn until here, right? So it should extend it. That's the unwell. Is that correct? Okay. And what's next? You have a flux. So active opens up flux. So when you fabricate a transistor in here, actually the flux is gone, but it should be here, you know. So from this side, you got a little flux. No, so this area shouldn't have any flux. So it's actually here and here. Because flux is only in a, so P select and P active, which one is larger? Remember from the homework, you got two boxes here, did you see? One is a solid gray color, another one is slightly bigger than that. Remember which is bigger? The active or the select is bigger? The select is bigger, right? Okay. So this is active layer, so open it up. And the select will dope materials in here in the opening and also a little bit here on the flux as well, but which is fine. Okay, it's just to reduce the misalignment issues. So make the select layer slightly bigger than the active layer. Even though there's a misalignment, you are still doping. You make sure you are doping the material to the entire opening here. All right. So what's next? So underneath this one, it doesn't have anything, doesn't have a P plus underneath it, right? Does it have any P plus under that? No, because the gate, the polysilicon blocks it, right? Okay. So what's next? Let's start from this side, from here. what you have. So on the top of Fox, you got a insulation layer, right? And then metal 1, and metal 2, and metal 3. So from here, starting from here, you got N well, and then nothing, because the only thing you have is pretty much just the poly, because this is a poly layer. So you have start having something in this layer. So you do have it. It's a pretty long stick. It covers the entire N well. It's even slightly longer. No, it's within it. So it's over here, but longer than the opening. So it's here, right? And to here. So that's a gate. Okay. And when it's closer to the other side of the drawing, like here, it has a via. So you don't have to draw the via all the way through it to the bottom, because there's nothing at the bottom. It's just drilling a hole to the top and connecting to the metal 1 layer. You've got a little metal 1 here, like this, which is this guy. Okay, so this is actually longer than it, because you can see this is outside of this overlapping area. This is more accurate, probably. Do you have metal 2 and metal 3? No. Okay, and this problem is also the homework, one of the homework problems, but I ask you to draw the other cross-sectional views, which is number 2 and number 3. Number 1, no, number 1, number 2, actually. So let's draw these two as well. Any questions here, by far? Yeah, because it cuts through it, so it should have metal 1, metal 2, and metal 3, right? With C5, they always have these layers, even though you don't have anything in there, but they still have that insulation layer in it. Can you tell where the Fox goes? Because the active layer opens up a Fox. See, this is active, which is smaller than the P select, which is the gray area in the middle, that box, right? It opens up Fox. Mm-hmm. And that would be showing the cross section straight to the poly. That's right. So nothing got dope. Yeah, that's a good quiz problem. I'm kidding. Don't want to go too deep in it. What's that? For cross section 3, are we not able to see the middle one on the right hand side of the 3? No, you didn't cut through it, did you? No, right? Mm-hmm. It's 3D structure. So what about number 1? Number 1 is here, right? That's a standard PMOS cross-sectional view. So now we can draw it just to the scale here, okay? So here's a substrate. I don't have space on the top to draw all the metal layers, but you should draw it, okay? So N well first, okay? We got N well. So we're doing this one now, okay? That's N well, no problem. What's next? It's a bottom-up process. So you can start from the lower layers and start going up. So do you have anything inside the unwell? Yes, you do. Because this layer, this active layer, opens up the Fox, right? So you have the entire opening here. It's not doping underneath the gate. Okay, so you have a gate. But for the rest, from here, starting from here, they are being doped. But it's here being doped. Why? Yes. So P select is the window that dopes the material to it, P plus or N plus, but you don't have to P select. P plus, P plus. What else I'm missing? Fox. Okay, so where's Fox? No, so this P active, the active opens up the Fox, so you already get the Fox removed. Here, right? Okay. Oh, the gate should be a little bit higher. Sorry, it should be that tall, right? It should be pretty thin, right? There's it's called GOX, gate ox. Yeah, they might be the similar, very similar material, but you couldn't really tell from the SEM. Remember last time? It's just a very thin layer of oxide running through it. So there will be a, we don't have to do all the details. Let's just treat it this way, okay? So this is the Fox. Make sense? Okay. And then this layer, there will be a via. See the poly, the P plus has a via connect to metal 1, right? So connects to metal 1. It drills a hole there. But this gate is in the middle of the second insulation layer here. So this gate is in here, okay? And on the top of it, that's the width of the metal 1. We have metal 1, metal 1. So that's M1 layer. And you have metal 2, you have to draw metal 2 and metal 3 layer, insulation layers, but you don't have metal 2 and metal 3 in there, okay? But so when you are drilling it, you should still draw it on the top. I don't have space, so. Question on this? P select is not really a thing, it's opening. So it's one of the process in the photolithography. It's just a mask. It's not just like you have a window here and then dope something in there. It's you probably have to. So there are so many details of it. It's all the process of coat a photoresist, right, and then etch it, and then coat the insulation, etch it, whatever. So all this process, eventually you have that opening available to dope. But when we are dealing with it, you just imagine there's a window on the top, which you can dope material through it. But there isn't such a window. Yeah, but it's not a thing, not a physical thing that you can put in there. You don't need a P select in there physically. You just need a P plus gate, well, that's it. That's a transistor, right? But when we are thinking about the process, we just treat the P select as a window on the top. It's easier to remember because you guys are not semiconductor, the process engineer in working the foundry. Hopefully, Dr. Jessing's semiconductor engineering, that engineering 430 or 431. So Connor was in that class.
Mm-hmm.
Did he cover all the details of the, like, how do you put all the layers on the top? It's a super complicated process for, even though only 3 metal layers. Yeah. It's just all the details, right? Yeah. Mm-hmm. It's just too much in there, you know.
So much. I know the lab was crazy.
Uh-huh.
Trying to do right now.
Yeah. Uh-huh.
Yeah.
But for this simplified version of it, does that make sense? We you guys just remember that the P select is the window that we can dope P plus into that window, and because you have a gate in here, so it's blocking P plus to reach the N well, so you got a channel, right? But you got P plus here. Okay. What about number 2? That's an easier one. So in number 2, do we have a P select or P active? For this one, do we have anything in there? No. So should we have an intact fox or a fox to be opened up? Yeah, you have an intact fox, right? Top. Do you have a while? No, it's outside of the while. So it's just basically it's a poly floating in the air, and then drill a hole on the top to metal 1. So which one is bigger? Which one is smaller? The poly is bigger. Metal 1 is smaller. So here's poly. Okay, to draw it here, okay, it should be, that's a poly's width. It's a poly. We have a very small square in the middle as a via, and then you have a smaller layer of metal 1. That's poly. That's M1, and you should have layers of metal 2 and metal 3 as well, but it had nothing in it. Right? Block fox, what does that mean? What do you mean by block?
I thought that when you put the, oh no, no, it's block, no, block.
Yes.
Not the active open.
And the fox is actually very thin. We drew it, make it visible here, but it's actually very thin. So you only have a very thin layer of oxide in the middle. So that's why the CMOS transistors consumes less power, because it doesn't have a direct contact with the pin junction here. So you don't have constant DC current flowing in the circuit all the time. But for BJTs, they are just junctions without any dielectric material in the middle. They have direct current or DC current flowing the transistor all the time. So it consumes a lot of power. That's why CMOS transistors getting more popular once it got invented many years ago, 40 to 50, 60 years ago. It used to be BJTs everywhere, like these ones. Probably have seen this somewhere, right? So these are NPNs transistors, just NPN materials. It's a junction, and you have a base, a wire here, a wire here, a wire here. You have to, so because it has a direct contact with a P junction, so direct is always flowing a very small base current in here. Whenever it's being used, you turn on here, so it's flow a lot of current in this channel to amplify the current. But the thing is, you can see there's nothing block it. So if you connect this one to the voltage source, always running current into it. But for CMOS transistors, it uses electric field instead of current to bias the channel. So it's actually accumulating. If you are using a NMOS, for example, it's attracting electrons to the channel. If you have a diffusion here, for example, like N plus, so the electrons are staying there; they're not moving around until you give a pressure to it. So saving a lot of power. Okay, in this case, we don't have this drawing. Don't want to confuse you guys. Any questions for this drawing here? No, not good. These ones. Draw a pin junction, I explain. So forward bias. So first, if you draw a pin junction in the depletion region, on the left-hand side, are you getting electrons or holes? Electrons. Keep in mind, don't get confused. So it's plus and minus and plus like this, because the electrons so the N junction has a higher concentration of electrons. So it's going to diffuse to the other side. So that's why on the other side of the depletion region, you are getting extra electrons. Same to here. You get more holes here, which the higher concentration of holes. So it's going to diffuse to the other side. So you're getting holes, more holes on the right-hand side of the junction. Don't get confused. And if you forward bias it, because you have plus, minus potentials on each side, and the anode is going to attract electrons. So the depletion region here is losing electrons, so it becomes thinner. And when it becomes thinner, and C equals epsilon A over D, right? So this drops, so the capacitance will increase. This cross-sectional view is just the two N wells, but nothing else, just N wells with different shapes. And this problem we are using, probably didn't rewatch the video, and we cover this. It's called, what's the name of it? Distributed time delay. I forgot the name of it. Problem. Yeah, distributed RC delay. Time to RC delay. And the equation is 0.35 times R square times C square times L square. So L is how many squares you have in the circuit. So this is from the notes. I derived it. Spent probably 20 minutes in the class to derive it. Just go back to the notes and look at it. This one. Okay. So this is what? N well. Draw it. Okay, so got an N well here. So that's metal 1, metal 2, metal 2. Via, do you have poly at all? No, it's just metal 1, metal 2. 2 vias. One on the top of the N well, one outside of the N well. So since you have an N well, Do you have a fox on the top or not? Do you have a unselect or p-select? You don't have the select layer, let's assuming you still have the fox on the top. They probably can dope that unwell first and then deposit another insulation layer on the top, right? Do you have poly? No. You have metal 1? Yes. So metal 1 is basically a long stick here. It's a long line. So do have metal 1. And metal 1 is bigger than the unwell. So if this is unwell, so it should be longer than unwell. So we have a little bit here and a lot on the right hand side, like this. That's metal 1, right? You have metal 2? Yes. You got metal 2 here, which doesn't have any via, doesn't make sense, just a floating wire. Okay. You got 2 vias. One is inside on the top, but inside of the unwell. So you got a via here and a via here, which is outside of the unwell. But the metal 1 is pretty big, like this much long. You do have vias, one here, right? Make sense? Yeah, I'm gonna scan it on to the website. So I've done this. What about this? Just did it with layers of all the layers, right? It's pretty simple. And why is the footprint of the unselect larger than the inactive? If you refer to the notes, actually wrote it on the notes, I think. Why the active layer is the select area is bigger than the active area. To minimize what? Misalignment. Okay. But do we understand what that mean? Everyone can read that answer, right? If you do understand, you can see the to minimize the misalignment, but to understand what's going on. Okay, so open up the fox, but you want to make the select area bigger to dope the material into the opening. So you don't have to, so you are not missing any of the area in the opening. Okay, so you open up the fox. That's the fox. So that's the active layers opening, right? But when you dope the material, you have a window on the top to, you just dump materials on the top, for example. That's how you understand it. You don't want to make the opening exactly the same size of the window or the opening here, right? The window shouldn't be the same size of the window here. You want to make it slightly bigger. So make sure all the material, all this area it's been doped. The polysilicon wire can be used as resistor. I think the resistance was, I forgot the number, but 20 or something. Well, 200 per square. So for poly in C5, poly's resistance is 200 ohms per square. So how to reduce the resistance of polysilicon wire? If you have to route the layer or route the signal using the polysilicon layer, and there's a way that you can deposit a polysilicide, right? It's called silicide on the top. Deposit silicide on the top of poly. So you can deposit a thin layer on it. to reduce the resistance. And the material is usually tungsten in C5. Okay, any other questions for the quiz and homework? That's good. Okay.
Switching point for inverters.
Inverter schematic. Input output. And we hope the inverter switches at 2.5 volts. So anything lower than 2.5 is considered as 0, or anything higher than 2.5 is considered as 5 volts or logic 1, because when you are using 5 volts logic for Arduinos, you must have realized that some of the sensors are being operated at 3.3 volts, right? But can still communicate with Arduino because 3.3 is considered as 1. It's larger than the switching point of the logic. So for example, here's a sensor. Here's Arduino, okay? Arduino. It's powered out by 5 volts. And you got a sensor powered out by 0.3 volts. Okay. So this is actually very practical. If the sensor is always sending signal to Arduino without receiving any of the voltage from this at all, will never receive voltage. So this is always sending, will never receive it, will never receive anything from the Arduino, which is fine. You can do this. You can connect the 3.3 volt sensor to the Arduino, which is fine. Because this one will send signal, which is 3.3 volts at the maximum, as logic 1, to this guy. So the transistors designed in Arduino can handle that logic 1, which is 3.3 volts, no problem. It won't damage it because these transistors are designed to run 0 to 5 volts digital signal, right? However, if the sensor is also receiving voltage or signal from the Arduino like that, it could be a problem. If the transistors designed in this 3.3 volt sensor cannot handle 5 volts, it's going to either reduce the lifespan of the sensor or directly blow it up immediately. So this can only happen when the sensor is just sending signal like temperature or something else to the Arduino, which is fine. But if you have a 3.3 volt sensor like also receiving signal from the Arduino, you should be careful about that. You should either open up the data sheet to look at the parameters here, see if it's able to handle 5 volts, or never do it. Or another option here is what you can do. What you can do here. So instead of directly connecting them, right? So you can add a voltage divider. Okay. So what are the values for the voltage divider? What's a good design for it? So when 5 volts is sending signal out, the 5 volts is being divided. So it's basically 5 or X, 3.3 volts over 5 equals R1, R2, right? Equals what? Mm-hmm. Yeah, and see what are the resistors available in the lab and pick up R1 and R2. Okay. But always pick up the resistors in the like 10K range. Even don't pick up like a 1K resistor because this one is always consuming power in the circuit. Right? If you have a very small resistor, it's gonna be a heavy load for the digital port. So it won't be able to drive this pin at a fast rate. If you have a pretty high frequency digital signal is running pretty fast, if you have a pretty small resistor here, it's going to cause a lot of problems. So always use a 10K range resistor in this circuit. So do you need anything here? From the sensor to the Arduino, do you need anything here in this at this port? Do you need to boost the signal to 5 volts? No. 0.3 volts is also considered as logic 1 because it's higher than the switching point, ideally. Okay, so how to calculate the switching point in the digital circuit? So inverter is just one example, but in the future, for other logic gates, you also use the similar way to calculate the switching point. So you should design the switching point in the middle or half of the VDD as much as you can. So how do we do that? I have to use square law equation in this case. So when it's switching, so this is the inverter's curve, right? So when it's switching, V in equals V out. Okay? And V in equals V out equals V switch. For SP, let's use SP here. So V in equals V out equals VSP. Okay? And because there is just one channel flowing the current, if we don't put any lobe here, it's just one channel. Okay? So if we calculate the current for PMOS and NMOS, they should be equal. And the voltages here, they are also equal because we are calculating the switching point, and they are all equal. So what's happening is to calculate the PMOS IDS or ISD here, it becomes VSG, okay, VSG, which is VDD minus VSP because V in equals VSP. So voltage here equals VSP. That's the switching point voltage. That's VGS. VGS minus VTHP square. I use beta P over 2. That's ISD. And then you can calculate IDS as well. So they are equal because it's one channel. It's flowing current from top to bottom. So IDS is beta N over V in. V in is also VSP minus VTHN squared. And to move things around, you can calculate VSP equals beta N over beta P, V times VTH N plus VDD minus VTHP over 1 plus beta N over beta P. So that's how you can, that's the value of the VSP or the representation of the VSP. And if we want this one to be 2.5 volts, okay? So switching in the middle. By doing that, because these are all constants, and this will give you this, beta N over beta P is somewhere around 1. So beta N, we know that is KPN over 2 width over length, right? And beta P is KPP over 2 and width over length. This N, this P. okay? And KPN equals 120 microamps voltage square, and KPP equals 40 microamps. That's from the textbook, okay? And in this way, we can find out the values for WN and WP in order to make it switching at 2.5. We're going to go through more details on Wednesday for this one, but we'll start continuing from here on Wednesday. But you can see that you can design the transistor size in order to make it switching at 2.5 volts. I'm going to run a simulation on Wednesday for you guys, okay? Running out of time, but we'll see you guys on Tuesday or tomorrow morning, and there might be a short lecture tomorrow in the lab. Be there on time, right?